Welcome to this explainer. Okay, look around you right now. The room you're sitting in, the device you're watching this on, the very depth of the space you inhabit. What if all of it, absolutely everything we experience in 3 dimensions, is actually just a 2-dimensional projection? I know, it sounds like pure science fiction, but it's currently the focus of some of the absolute brightest minds in theoretical physics.
So, this brings us to a seriously wild question. Is our 3D universe actually just a 2D hologram? It's a mind-bending thought, isn't it? But to answer it, we're going to explore a bleeding-edge framework called celestial holography. We'll break down the math, the physics, and exactly how celestial holography works today in the global race to uncover the true nature of reality.
Okay, let's dive into this. We're taking this journey in 5 steps. First, the hologram hypothesis. Second, gravity versus quantum mechanics. Third, decoding celestial holography. Fourth, the infrared triangle. And finally, the future of physics.
Part 1. The hologram hypothesis, swapping a messy 3D room for a 2D blueprint.
So the core idea here is that all the information making up our 3D universe could actually just be encoded on a lower dimensional boundary. Dr. Sabrina Pasterski, a leading physicist and founder of the Celestial Holography Initiative, hit the nail on the head. She says, celestial holography says you don't have to watch the whole 3D universe play out. You can read it all off that flat 2D pattern on the boundary. I mean, think of it like sitting inside a giant glass globe. Instead of trying to track every single tiny object floating around inside, you just read the 2D pattern cast onto the inner surface of the glass. It's a brilliant way to picture an incredibly abstract concept.
Moving right along to part 2, gravity versus quantum mechanics, the biggest unsolved problem in physics.
Now, you might be wondering, why do physicists even need a radical new framework like this in the first place? Well, it all comes down to the fact that our 2 best scientific theories literally do not get along. On one side, you've got quantum mechanics. It brilliantly explains the subatomic world of particles, but it completely breaks down when you try to apply it to cosmic scales. Then on the other side, you have Einstein's general relativity. This flawlessly explains gravity and massive cosmic structures, but fails entirely at the tiny quantum level. Finding a way to reconcile these 2 titans into a single unified theory of quantum gravity is pretty much universally regarded as the ultimate holy grail in physics today.
All right, part 3, decoding celestial holography, mapping spacetime to the celestial sphere.
Now, what's really interesting about this concept is how the math actually functions. First, we need to talk about the celestial sphere. In physics terms, and stick with me here, this is an imaginary 2D surface located at the boundary of what's called future null infinity. Basically, it's the absolute ultimate boundary of our flat spacetime. Remember that giant globe metaphor we used earlier? This sphere is exactly that. It's the inner surface of the glass where all our 4D spacetime information gets projected.
Next up is the S-matrix. This is basically the mathematical framework physicists use to describe how quantum particles scatter in our standard 4-dimensional bulk flat spacetime. It's how we measure particle interactions right now. But here's the massive challenge for celestial holography. How on earth do you take all of this complex, messy 4D data from the S-matrix and perfectly map it onto that flat, clean 2D celestial sphere?
Well, here is the actual mathematical sequence of how they do it. Step 1. Particles scatter in our 4D spacetime, which gives us our S-matrix data. Step 2. Physicists bring in a heavy-duty mathematical tool known as an inverse Mellin transform. And Step 3. That transformed information successfully becomes conformal correlation functions on our 2D celestial sphere. The underlying math is incredibly dense, but the takeaway is just elegant. It essentially removes the problematic force of gravity from the equation entirely. You're translating a messy 3D gravitational problem into a much cleaner 2D quantum blueprint.
Which brings us to part 4, the infrared triangle, the framework constraining the S-matrix.
So what is the infrared triangle? It's a triad of deeply connected physics concepts that completely underpins and constrains the foundation of celestial holography. At corner number 1, you have soft factorization, which specifically deals with low-energy particles. At the second corner, we have gravitational memory effects, and at the third corner, asymptotic symmetries, things like the BMS group, which act as strict conservation laws. Working together, these 3 corners beautifully link quantum field theory, space-time geometry, and the conservation of charge.
But this is where it gets absolutely wild. Let's look a little closer at gravitational memory.
When incredibly massive objects, like two black holes, collide, they don't just send out temporary ripples. They actually leave a permanent, measurable imprint on the fabric of space itself. This isn't just chalkboard math anymore. This is a real, tangible, observable signature we can look for in our universe to prove that these massive gauge symmetries actually exist.
Finally, Part 5. The Future of Physics. Global Initiatives and Real-World Testing.
Because of that potential for real-world observation, this theory is moving way beyond theoretical musings. Today, heavily funded global efforts are striving to test this. Major institutions like the Simons Collaboration and the Perimeter Institute's Celestial Holography Initiative are leading a massive global research effort. We're talking about the brightest minds from places like Princeton, Harvard, and Cambridge teaming up to figure out exactly how celestial holography works today. Their ultimate goal? Pinning down a universal quantum gravitational physics framework.
And check out this specific number, 200,000. Right now, researchers are exploring this fascinating intersection between geometry and number theory. Specifically, they're looking at a fractal interface at a phase transition scale of around 200,000. What they're attempting to do is directly link the strict, ordered rules of number theory to the literal texture of the celestial sphere. They want to see if this specific scale is the mechanism that smooths out the totally chaotic quantum vacuum into the nice, smooth spacetime that we actually observe.
So what are the active frontiers where scientists are working right now? First, they're testing the theory against actual gravitational wave observations from detectors like LIGO and the upcoming LISA mission. Second, they're jumping some highly technical math hurdles, like resolving the soft omission problem, which is where traditional math accidentally discards zero energy contributions. And third, formulating new rules like a non-perturbative bootstrap to better define the 2D celestial conformal field theory. Essentially, they are working tirelessly to move celestial holography from a purely mathematical hypothesis into an observable physical reality.
Which leaves us with one final deeply provocative thought. The next time you look up at the vast, deep, three-dimensional expanse of the night sky, ask yourself, are you really looking into an infinite void, or are you simply reading a flat, two-dimensional pattern perfectly encoded on the boundary of the universe? It's a question that might just completely redefine our reality. Thanks for joining me for this explainer.